Okay, are we live? Okay, I guess we are. Okay, so this is kind of one of those streams that seems to be the thing that people do nowadays. So I'm just gonna make one where I hope to to show a little overview of the Rust embedded development. There doesn't seem to be plenty of information about it right now, so I hope it's going to be helpful for someone to start messing with this stuff. So for this, the gear that I'm going to use is the little STM32. This little dev board is called Bluepill, and you can just buy it for a couple of bucks. It's quite cheap and more than enough to start messing with it. And we're going to use the it's called ST-Link. This is ST-Link version 2. It's just in-circuit programmer debugger from ST. Yeah, and again, it's quite inexpensive and works perfectly. And to program all of this, we're going to use something called OpenOCD. It's quite mature and quite popular software for programming microcontrollers. So it's most likely is going to be available from your repo. But if not, I guess just googling it should result in plenty of hits, and then just go ahead and install it. As you can probably see, I'm working actually on Linux, running Sway. So if there's any issues with the stream, yeah, I can promise it's gonna work smoothly. Not to mention that I don't do many of this stuff. So basically we're just going to start from creating a project. Basically we're going to go ahead and use cargo for this. And what we're going to do, cargo new the messing. So this is essentially just a bog standard Rust repo or Rust project. So we're going to have to add a couple of things to turn it into the embedded project. So first of all, let's add a couple of dependencies. So basically we will need embedded hall, and we need to check what sort of version it is on currently. Okay, so we're nearing version 1, but I guess let's go with this because we don't know if the rest of our libraries are going to be working nicely with this. So let's go with version 0 to 4. And then the next thing is the actual library, or the HAL library that we need for our processor. So basically the STM or the blue pill is using the STM32F103 microcontroller. So we need to find a HAL that will work with this. So basically we're looking for something like that, but it's going to be more like STM32F. Yeah, something like that. Nothing found. It's going to be this. So yeah, I guess we can just go with the latest 07. Yes. Is that what it was? That's going to be easier. Okay. So we're going to let this crack on. Okay, so what do we have here? So actually you can see our blue pill board on the diagram in here, and it's actually going to be quite useful because it's showing us some of the pins that we're going to use. So I guess obviously we're going to start with blinking LED. So one of the LEDs, the red one, or actually no, the green one, we're going to try to blink it a couple of times, as you know, that's the embedded equivalent of hello world. So we are going to be using this OpenOCD. As I said, we're gonna need a target installed. So I already have all of this on my system, but basically in order to add the target, you can use the rustap command, such as this, and rustap will install all the targets for us. You can go HF for a floating point target. That's for some of the boards that have a floating point support within the chip. Do we have the floating point in here? Yeah, it doesn't. Yeah, it doesn't seem that we have a floating point calculation support. So we're just going to go with the standard one, which is this one. So if you don't have it installed, this command will install it. And then again, if you guys need OpenOCD, like that's how you do it on the Arch. So and that should install all of the stuff that you need to run it. I'm not going to do this because I already have it. And I think for actually for OpenOCD you might need the libUSB libraries as well, so that's how you can install it if you want to, or if you need to. So no package named embedded hull. And why is that? There should be an embedded hull. Oh, typical. Yes, that's better. Okay, so we're just going to start cracking. So basically, we're going to start with flashing the LED. Okay, and actually, yes, those guys, they're extremely important as well, and without this we won't be able to do anything actually. So basically Cortex-M and Cortex-MRT, that's a bunch of libraries that provides the definitions for the absolute low-level peripherals that exist on the STM32. So we definitely need those. But we can double check if those are the latest versions or not. So 064 and 0613. There. What's going on here? Ah, yes. So basically this thing. So what this means is, because basically you have a whole bunch of ARM devices that corresponds to this series essentially. So basically you can have 103, one something else. So we need to specify explicitly which processor we're talking about. So as I mentioned, the blue pill is using STM32F103 and then something else. So we need to explicitly enable the this feature within this packet. F1 XX hull. So we go with the version, which is the one that we specified, 7, but we need to specify the features, and that's what will enable the actual support for our chip. So we're looking for STM32F103. And actually I think we need to specify the range of the processor. So basically those processors, even with the same serial number, however you want to call this, there are actually subtypes as well which differ in the amount of peripherals they come in equipped with, and flash sizes, RAM sizes, stuff like that. So this, as far as I remember, is a medium range. And if you're not sure, this is the way to check it. So basically that's our processor, but this is the reference manual, and that's actually very important document, because that's where you're going to find all of the information about peripherals and how to configure them and use them and stuff like that. But we need this datasheet. So, and that's the actual chip that we have it. So in our case it's C8 RTG, I think, something like that. So basically, description probably. So yeah, those are medium sized or medium density performance lines. And yeah, so medium. And hopefully we should be able to compile this now. Yes. Okay, so we're getting some sort of load on our system, but we'll see how we're getting on. So meanwhile, we can start. Oh yeah, the panic hold. So basically, this is a handler for the panic state of our processor. Oh yeah, and RT as well. We should have just read the GitHub README. There. So we're going to have a look at the examples directory. So Blinky. Just gonna copy the code. And as I said, since they're using the blue pill for this, we can just almost copy it verbatim and it should just start working. So for that we need to open the main. So obviously the traditional main is not gonna work in the context of the embedded stuff. So here we are going to have to make some changes. So basically, yeah, let's describe the difference. NB block and panic. Okay. So we need NB, and again the version is version 1. That's straightforward. And we need panic hold. So basically this panic hold, this is a type of oh no, what I'm doing. So this is a handler that's going to tell the processor what to do in case of a crash. So for our initial development, that's good enough. So basically, is just going to, I think, stop our processor in one of the exception handlers that's inbuilt within the processor. But we can check that in a second. Panic hold, that's a version 0.2.0. Yeah. Because yes, there. This underscore hyphen stuff in Rust is pretty annoying. Okay, so let's see what we have here. Unresolved input. This is silly. There it is. So this is our panic handler. That's good enough for what we're doing right now. This is the non-blocking library that we need for the timers, because basically it looks like the embedded community is reaching some sort of consensus where they want to use this non-blocking result for all of the timer operations. I'm not exactly sure which direction this is going, but I guess that's what it is for the time being. So what we have in here, we need to tell the compiler that we are not using any standard library, and we don't have a traditional main within this program. So basically what is happening is that, and for this reason, that's my baby. So for this reason we need to specify, or we need to mark a function that's going to be well, that's going to be basically called in when the software where the code execution starts within the processor. So that's where the when the processor starts, that's where it's going to jump after all of the initial preparation that it has to do. And we do this using this entry. Yeah, so this is basically the library, the Cortex-M library that we had to add to the project. This contains the descriptions of the low-level stuff of the STM processors, and then this comes, as you can see, from the actual HAL library for this specific chip. This is a bog standard kind of initialization routine for those processors. This performs the configurations of the clock on the system. So by default, this is going to use the internal oscillator that comes with the STM chip itself. So it's just a resistor capacitor kind of circuit that drives the clock for the entire processor or microcontroller. If we would want to, we can specify additional stuff in here, like for example a specific H clock value, or the peripheral clock 1, peripheral clock 2, the system clock, ATC clock. That's the I guess that's for driving the clocks when we're using the analog to the digital conversion pins, when we're reading some analog values from the system or from the external components. And then this will tell to use the external oscillator if you would like to use one. So for example, the STM blue pill actually comes in with the external 8 megahertz crystal. So we could use it if you want to, but I'm not going to use it right now because we're just trying to run a simple example. So yeah, so basically once we run the freeze, that's going to finalize the clock configuration for the chip, and we're going to be given a struct that contains the clock configuration. This is essentially this is actually a stuff that we will need to use for any of our timer configurations later on. I'm not sure what would happen if we were to use multiple system timers, but I guess we'll see once we get to it. yes, we're initializing the Gpoc peripherals. So normally on the well, it's happening different in a different way for different processors, but in general, for ARM microcontrollers, you need to initialize it each peripheral that you want to use separately. So that's basically what we're doing in here. We're initializing the Gpoc port register, and we need to specify the APB register to do so. So basically what will happen in here is that you're going to, well, for this I'm not entirely sure, but I guess you need to specify the clocking and enabling of the peripheral and stuff like that. Not 100% sure here. I guess this has more something to do with the way Rust handles the ownership of the different data in variables. Yeah, but basically once we have this Gpoc, we have the C port enabled, and basically the Gpoc means the actual port of the processor. As you can see, for example, or yeah, actually even in here, notice here that you have a PB, a series of PB pins, a series of PA ports, PB again, PC. So each of those letters, A, B, C, D, on different processors, that actually describes an entire port that can be used. This is needed for some, let's say, parallel reads or writes that you can perform on to the different peripherals you might be interfacing with. But we only going to be using this one PC13 LED. So there's something else connected to it, but I guess we don't have to worry about that, because as far as I know, this hooks in directly to this LED. So what is happening in here? Yeah, that's where the actual or configuration is performed. Oops. That's where the configuration is performed. We specify the pin which we want to use, and we configure it as the push-pull output. Yeah, and we need the Gpoc CRH register handle to do it. And then, so once we have this pin configured, essentially as a LED, we configure a timer. So this timer is a syslog. That's what it's called? No, I think it's a system timer, SysTick. I think it's called SysTick in ARM. Yeah. Yeah, that's basically a general purpose system clock that you can use for creating delays and stuff like that, and it's completely separate from all the other timers that are available from the STM32 at least. So as you can see, this guy, it actually, well, not specific this device, but this series of microcontrollers can go as far as, looks like 14 different timers, and they will all differ. Well, not all, but there will be sets of them which differ in terms of functionality. You can configure them as outputs and inputs and counters, PWM drivers and stuff like that. This specific one has how many? 7 timers, 3 16 bits, 1 16-bit PWM driver, and 2 Watchdog timers, and a SysTick. Yeah, actually I forgot about Watchdog timers as well. That's another set of functionality that you might need. So basically, Watchdog timer is a timer that you enable on the system, and you have to explicitly reset it every certain amount of time. If you fail to do so, it will cause the reboot of the whole processor. Well, not necessarily reboot. It could be just like raising an interrupt or something like that. So basically, this is a method of helping you perform recovery of the system in case there's some sort of like a glitch or you end up in some infinite loop or whatever. It's kind of like a security mechanism. Yeah, so at this stage, at this point of the code, we already have the timer and we have a LED, which are two things that we want to do, which is basically be able to measure time and change a pin value. So we can save, we can build it. Yes, I did mean that. Okay, and here we're getting into the language specific stuff. So basically what is happening is that we need to tell the Rust compiler what target are we using for the compilation, because essentially what we're doing in here is we're actually cross-compiling a binary on one system into a different system. So Cargo has a method to do so. We can specify a Cargo directory, and in there we can specify a config file. It's config there, and in here we need to specify we can specify the target that will tell the compiler, how to perform the actual compilation. So we can do this with Cargo build, I think, what was it, target, and then of course I won't remember it. We can look it up. It was Rust up, yeah. It was this. There. And as you can see, it actually starts compiling it, but there's a better solution slightly, where we can specify what we need, basically tell the compiler what to do during the compilation, and then we don't have to specify the full command. All we can do is then basically Cargo build, and it will do everything for us. It just save us typing, but of course I don't remember what that exact what the actual content of this should be, but we can just check it out, and we should be able to check it out in here. Yes, so that's what it is. There. So runner GDB multi-arch. So in our case, that's not gonna work. We need to use the ARM non. What is it? It's ARM non EIB GDB. So basically, if we're running the if we go cargo run, that will run this runner command. If we go cargo build, it's going to look at the Rust flag and the targets and stuff like that, and the build command, and apply those settings to the compilation. So that should already help us a lot. So if we go cargo build, that's actually starts running the compilation process according to those rules. Yeah, so like I guess now we just wait for the stuff to finish. It's gonna take a while. The compilation process is not the fastest on or in Rust. Okay, so this is, yes, so this is me being silly, of course, because I was looking at it and I forgot to do this. Basically this command Rust flags, that passes arguments to the linker. So basically what this means is that the compiler is going to look for a file called memory X, and that memory X file, that's that needs to contain the memory layout of the chip that you're compiling the program for. And by memory layout we mean the RAM location and the flash location. So let's just create it. Memory X. Okay, so this is essentially just like a linker script. You need to create those for you know, if you're developing with embedded C and C++ stuff as well. If you at least if you do this manually, kind of like here. If you're using, you know, all of the available embedded development IDs, they usually do this, or this software usually compiles this or generates this file for you. So actually I don't remember, can we find it here? Yes, it is. So we can copy this, and I kinda know that this is correct. But if you had a different chip and you didn't know where to get those values from, so basically you can check it up in here in the datasheet. So actually in this one, the actual datasheet of the chip that you're using. If you go, well, basically it describes you the size of the chip, and to be honest, I'm not sure for those. I never found a clear answer if the flash memory is 64 or 128 kilobytes for those chips. So I believe it's 64, but I have no idea to find to like explicitly get that information from the datasheet. I don't know what is the marking on the chip that will tell you exactly which one you're going to use. So it's slightly better in this case to go with the lower value, because if you would go to the higher with a higher value, you could actually cause some issues later on. If it turns out that your chip only has in fact 64 kilobytes, and the SRAM is 20 kilobytes. So if you go to the memory mapping, that will actually tell you exactly where the memory is located. So we can see that the flash memory actually starts at 0x08000000, blah blah blah, which is this origin. And the length of it is actually 64K. And then if we want to check the SRAM value, we can see it in here, and the memory address that it starts at, which is again this. So if you didn't, or if you were to create this file manually yourself for your specific chip, this is the information where you're going to find it. Again, those documents, they're actually, you know, it's good to be familiar with them, not to know them, but at least be know more or less where to find the information. Like, there's no way that I could keep that information in head, you know, but once you know where to reach out for the information, it's fine. Okay, so we created that script, we saved it, and now we should be able to just finish the building, and there it is. So our target is actually the output file is located in the target, and then what did we? Oh, I copied the wrong version at some stage. So we are actually in temp v7m. Yeah. In debug, and that's our actual binary file that we're going to load into the processor. So what we need to do now is to hook it up to the PC or to your laptop. So that's plugged in. The power right now, the external power is disconnected, so the only power that the board gets from is from the dongle. So ls USB shows us that the dongle is connected, and once we have the OpenOCD installed, I have this version, but you might have a different ones. I'm sure it'll work as well. The support for those ST-Links dongles been there for years at this stage. So anyway, or actually one thing that I mentioned, when you open or install the OpenOCD, you will have a bunch of scripts installed along with it, and those scripts are going to be located in user share OpenOCD directory, in the scripts directory, and in there you're going to have a bunch of scripts for different boards, chips, CPUs, interfaces, or targets and stuff like that. Like because there's plenty that you can do with the OpenOCD debugger, but in our situations, all we care about is the interface, and the interface is basically the dongle that we're using. So in our case, it's the ST-Link version 2. And the other thing we care about is the target. And in our case, again, that's going to be this, because we're essentially just programming a raw ARM chip. if we had some sort of like a discovery board or something like that, I think we could probably go with board, I guess. Yeah, so you can see, for example, like a beagle bone, the discovery, nucleo, a whole bunch of those. But yeah, we only care about the interface or the target. So open OCD, and then we need to specify the F, and then specify the interface. So I ran this command previously, and this is basically what we used. The open OCD will resolve the initial path to user share open OCD by itself, so you don't have to specify the full path of it. Just the directory within the scripts directory. So this is our target, and this is our interface. And if everything is correct, or if the dongle is correctly connected with the blue pill, once we hit enter, we will connect to it. And you will know that you're connected by rapidly red-blue flashing on the dongle. So yeah, this hanged, which is correct because it's actually connected to the board. What we can do now is to flash the actual firmware into the board. So okay, I kind of mentioned it, but I didn't say it explicitly. You need arm debugger to load and run the software in here. And again, you can, it's going to differ on your system, but for example, pacman and armnon eabi gdb command is going to install it on your system. You only need the debugger. So this command on its own is going to start running the debugger, where you actually need to connect to the chip. And then you can load the target. That was M, debug, and the messing. When the target is none. We need to. Oh yes, sorry. We need a target. So that means we need to connect to the chip through the OpenOCD debugger. So, and the target is remote, and it's running on the port 3333 by default. How do I know this? I know this from experience, but I don't remember where to find it. I think it's one of the interface chips. We can check it in a second, but basically by default it's running on this port, and boom, we can see that we connected to the chip itself. That says that the chip is actually 64 kilobytes, which is fine in that case. So we configured it correctly. And now we can load the target. Now we're loading the actual firmware. Oh, That's because we didn't specify the source. We will fix that later. Okay, we do that again. This target remote port 3333, and now load and the book, domestic. Boom. C means continue, so we are continuing, and as you can see, the yellow LED starts flashing according to what we put into the code itself. There. And then once we reset it, still working, which is good. Okay, but this is kind of well, not convoluted, that it's the way you do this, but it's kind of a very, very roundabout way of doing this, so we can, you know, improve the workflow a little bit. Let's leave this for a while. What we can do is we can create a little file within our project directory. And actually this one as well. So let's start from that. So OpenOCD config. Basically, whenever you run the OpenOCD, you need to specify this entire command with all the arguments, which will tell what interface to use and what target. We can we can simplify this a little bit by specifying the OpenOCD config file. In here, we need to specify just 2 lines of code, because every configuration file within the OpenOCD environment is a tickle file. So you can put it's a subset of tickle commands. So you can perform some, you know, complex enough scripting. But in here we are actually just going to be very simple. We're going to use a find command along with the interface that we need, is the link v2 cfg, and the second one is find target STM32. And I think that's it. So now we can connect to our chip simply by running OpenOCD. What happened here? Interface stealing, blah blah blah. Let's have a look. We need to use a source. There it is. That's the. You can check in here more or less what commands and how to do the scripting. I'm not sure where is it defined fully, but it's not a full tickle. It's just a subset. adapter speed is not selected. Target interface. What's wrong here? F1x. Oh, it's just 1x. There it is. So yeah, now we just need to run OpenOCD, and that will read the config file and connect to the chip. And we can do the similar thing for the debugger, because the GDB takes in a little configuration file as well. So we can do the similar stuff, GDB. And here we're going to speed it up a little bit and just do it in here. So we don't need all of this. We're just gonna take this. Target monitor arm has semi-hosting enabled. We're going to have to load as well, and then step. But actually we don't need a step, we can continue. We can continue and we're going to break on main. So basically what will happen is, as you remember the steps when we connected manually using the GDB, we connected to the remote target, which is the OpenOCD debugger. So this command that actually enables some monitoring, so I'm not sure, so we're just going to get rid of that, and we can add some other useful commands later. Load will load the firmware in there. That will set up a breakpoint on the main, and we just run the code. So the code starts executing, goes through all of the initialization, and then it will break as soon as it hits main. And one other thing that we can do is specify the file command and specify the path. Specify the path to our binary, so basically that we were going to load it straight away once the debugger starts. So that's essentially the path. There. So if we did everything correctly, we can just go and specify this, and then specify the option X, specify the file, and nothing happens because we don't have our debugger running. So let us start the OpenOCD here, there, and now we can run this, and boom. And as you can see, we reached the main, and we set the breakpoint as we told it to. And here we can actually specify have a look at the code that we're running. So if we run a step, we can see that we can step through the code. And actually step will step into the functions as well, so we want something less granular, so we're just going to use our next to go through the code. Next will just jump over the statement, but it won't go into the code, as you can see in a second. So there, we are back in the main. So there it is. And once we get into the loop, we're just going to go through that stuff. We won't be able to step through it. Well, eventually it will, but it's gonna take a long time. But basically this is the whole idea. Okay, so I guess once we have the flashing going, maybe we can go into a little more advanced example, or we just do it later. How long we've been doing this? Okay, that's 1 hour. Okay, I guess that's a good place to make a break. Okay, bye bye.